Okay, we'll return to inequalities a little bit later. Right now I wanted to talk to you about solving systems of equations, but this time we're going to talk about nonlinear systems of equations. Now when I say nonlinear, that means at least one of these equations is going to represent a graph that is not linear. So let's take a look at this first one here. So you can use a couple of different methods here. You can use the old substitution method or the addition method, whichever method you like, but what you want to do is try to figure out a way to eliminate a variable. So here what I'm going to do is I'm actually going to take the second equation, 3x minus y equals 4, and I'm actually going to solve that for y. And you can easily solve that for y. Just trade sides with the y and the 4, and you'll get y equals 3x minus 4. Now, the first equation said y equals x squared minus x minus 1. Well, I can substitute the 3x minus 4 from up here into that, and then I'll get this equation. Now, since it's already got the squared term on the right, I'm going to work from the right. So what I want to do now is, since this is a quadratic, I want to subtract 3x from both sides. So if I subtract 3x from the left, it'll disappear, and if I subtract 3x from the right, I'll just get minus 4x, which I got right here. And then I want to add 4 to both sides, so if I add 4 to the left, it'll cancel that, and then when I add 4 over here, minus 1 plus 4 will be 3. So now I get a quadratic equation. And fortunately I can solve this because it factors nicely into x minus 1, x minus 3. And then if you set those factors equal to 0, you'll see that the x values are 1 and 3. Now here's the catch. Each one of these x values is going to have a corresponding y value. And so we're going to have to go back to one of these equations and figure out what they are. I could use this one, but I'm going to use this one. That one looks a little bit easier to solve for y, so I'm going to use that one. Y equals 3x minus 4. So if I evaluate y at 1, I'll get 3 times 1 minus 4, which is negative 1. And so that means if x is 1, then y is negative 1. Then if I evaluate this y function at 3, so plug 3 in for x, I get 3 times 3 minus 4, which is 5. So I get 3, 5. Now it's not necessary to graph these to find the solutions, but I went ahead and did the graph for you here, and you can see that you knew one of the functions was a quadratic function, so it's a parabola, and the other one is a line. And notice that the solutions are simply where those two graphs intersect, and they intersect at the points that I gave you, the point 1, negative 1, and the point 3, 5. Okay, let's take a look at this one. This next one, I could solve it using the substitution method, but that would require me solving for one of these variables, and it would involve me getting some square roots, which would probably be a bit of a pain. So what I'm going to do is I'm going to just try to use elimination method and see if I can eliminate a variable. Well, when I look at this, I see that I have 3y squared here and 2y squared here. So if I were to multiply this first equation by negative 2, this term would become a negative 6y squared. And if I multiply this equation by 3, this term becomes a positive 6y squared. And then when I added them together, they would cancel. So I need to multiply everything in the first equation by negative 2. So multiply everything in the first equation by negative 2, and that'll give me negative 8y squared minus 6y squared, negative 8x squared minus 6y squared minus 96. And then I multiply everything in the second equation by 3, and that'll give me 9x squared plus 6y squared, and then 3 times 35 is 105. Okay, now I can add the two equations together, and when I add, you just add term by term. If I add the x terms together, minus 8x squared plus 9x squared is just x squared. the minus 6y squared plus 6y squared cancels, and then minus 96 plus 105 is 9. So now I get a simple quadratic equation, x squared equals 9. And so you know to solve that, you actually have to take the plus or minus square root of 9, and that's actually going to be plus or minus 3. So for each of these x values, there's two x values, there's negative 3 and positive 3. So for each of these values, I have to plug x into one of these two functions up here. So I'm just going to plug x equal negative 3 into the first one. Now if I plug negative 3 into this one, negative 3 squared is 9, so I get 4 times 9, which is 36. And then just bring the 3y squared and the equal 48 down. And then I can subtract 36 from both sides, and I get 3y squared equal 12. And then divide by 3, and I get y squared equal 4. So y equals plus or minus the square root of 4, which is plus or minus 2. So what that means is, that means that if x is negative 3, the y value is 2. And if x is negative 3, the y value is negative 2. Now, what's interesting though, if you go back and look at this problem, you'll notice that it's not going to matter whether I plug negative 3 or positive 3 in here, you're going to get the same result. Because when you square negative 3 or positive 3, you're going to get 9 either way. So for positive 3, so if I use positive 3, then I'll get two more solutions, 3, 2, and 3, negative 2. So basically I get 4 solutions. Now you may not be familiar with these types of equations, but these are ellipses. These are both ellipses, which is just sort of an ellipse is kind of like an egg-shaped, it's kind of an oblong circle. So an ellipse could be turned that way, or an ellipse could be turned this way, but notice it's easy to find two ellipses that intersect in 4 places. So that's what we've got here. Now I'm only going to show you the top half, but here's where they intersect here at negative 3, 2, and they intersect here at positive 3, 2. But also in the lower half down here, they would intersect at negative 3, negative 2, and positive 3, negative 2. So that would be the other two solutions. Now this next example is an example where you don't get a solution. I'm going to try the elimination method again, but let's watch what happens here. Here I can multiply everything in this equation by negative 4 so that I can get the x squareds to eliminate. And so when I do that, I'll get negative 4x squared minus 4y squared equal negative 100. And now when I add these together, I get 5y squared equals negative 64. So that would mean that y squared would equal, let's see, I got a typo there. That actually should be negative 64 over 5. So actually y would be plus or minus the square root of negative 64 over 5. But it really doesn't matter, because the point of this is to show you that you're not going to get a real solution. So I'm not really concerned about this. There's actually going to be 4 non-real solutions, and so the non-real solutions, the reason you're getting non-real solutions is because these are the graphs. One is a hyperbola that looks like this, and the other one is an ellipse that falls within the two pieces of the hyperbola so they don't intersect. Okay, let's back up on this example. You'll notice I actually changed it. So take a look. All right, so I made a couple changes here on the second equation. So now let's start this one again. So if we multiply this equation by negative 4, we're actually going to get negative 4x squared minus 4y squared equals negative 356. Now if I add these two together, the x's cancel. I'm going to get 5y squared equals negative 320. And then if you divide 5 into negative 320, you get negative 64. And the square root of negative 64 is not real numbers. It's plus or minus 8i. Now we can go ahead and solve this. If we plug plus or minus 8i in here for y, we get x squared equals 64i squared equals 89. Well, I squared is -1, so that's going to be x squared minus 64 equals 89, so x squared equals 153. And then 153, so x would be plus or minus the square root of 153, which is plus or minus 3 square root of 17. So that means there's actually 4 non-real solutions. There's 3 square root of 17 with minus 8i, minus 3 square root of 17 with minus 8i. There's 3 square root of 17 with plus 8i, that should be a plus 8i. And then there's minus 3 square root of 17 with plus 8i. So, but since these are non-real, all 4 of these are non-real solutions, that means there's no intersection. And if you actually graph this, you would get a circle that's completely inside an ellipse. And so the two do not intersect. Okay, freeze the video and write this problem down and try to work it using substitution is probably your best bet. And then see if you get the solutions I got down here. And you can start the video back and check your solutions when you're done. Okay, let's do one more. This time I'm going to do one involving a log, or actually 2 logs. So here we have y equal natural log of x and y equal natural log of 2x minus 5. Well, if I set these equal to one another, I get natural log of x equals natural log of 2x minus 5. So using substitution. Now I can subtract this from the other side, so I can move this log over to the left and it becomes minus. Now, if you'll remember your log properties, the log of something minus the log of something, if it's the same base, which these are both natural log, can be written as the log of their quotient. So I know now that this log can be written as the natural log of x over 2x minus 5 equals 0. Well, let's see what that tells me. Remember, this base right here is understood to be e. And so if you write this in exponential form, you get e to the 0 equals the argument x over 2x minus 5. Well, that's just 1, right? So that's just 1. So if I multiply both sides of that by 2x minus 5, 2x minus 5 times 1 is just 2x minus 5, and then over here it'll cancel the 2x minus 5 and I'll just get x. So now I can easily solve this. 2x minus 5 equal x, just subtract x and get x on the left, and then add 5 to both sides to get 5 on the right, and you get x equal 5. And then all you have to do to get the y value, this is easy, just go back into either this one or the second one. This one's the easiest one, and plug x equal 5 in, and you get y equal natural log of 5. So the solution is the point x equal 5 and y equal the natural log of 5. And so that's where the two intersect. This next one is just to show you that sometimes there's no way to solve it, because if I tried to solve this like I did over here, I would get e to the x minus 3 equals log x. And actually I didn't do substitution. I did elimination. If you tried to subtract here, the y's would cancel and give you 0, and then when you subtract here, you get e to the x minus 3 minus log x. So there's not really a good way to solve this algebraically, but if you look at the graph, you can see that you do have 2 points of intersection, one right here and then one down here. So sometimes you have to use other methods to solve for solutions. So I just wanted to show you that one, just to show you that sometimes you might have to use some sort of numerical method to solve for the solutions for a system of nonlinear equations. Okay, so that pretty much ends this section. I do apologize for having to correct that one up there, but we finally got her straight. So have a good day.